Good morning to those outside the curtain. I know there's wonderful coffee and croissant out there, and you can bring them inside. And I am going to reiterate, because of the strength of the lights, for anybody who hasn't stood on stage, we really can only see the first couple of rows. And also, the sound in this room is a little bit tricky for the speakers to hear back. So if you're asking questions at the end of their talks, it is also much easier. So it's a double win for all of us if you can sit close to the front. And particularly with the numbers today, I'm trying to kind of think about the calculation, how many chairs per person in the room at the moment. So we've got a wonderful first session, a really wonderful first session. It is Architectures and Future Vision, and it's going to be chaired by Stefania Pandolfi from ISA, of course. So Stefania, welcome to the stage. And please give her a big round of applause. And definitely we have to make 10 times the noise, because at the moment, there's not so many people in the room. That party last night must have been very, very good. And you also must have been very, very good to either party hard or go to bed early and be here on time this morning. So thank you very much. Stefania.
Hello, hello. Do you hear me well? Yes? All right. Given the number of participants, the party was very good last night. So, all right, let's get going. So, welcome our first speaker, all the way from Australia. Nick Barnett. All right. Nick is from Interstellar Mapping, and he's gonna get about enabling sustainable lunar water ice utilization, halfway there, through integrated mapping and ICRU system. Welcome.
Thank you very much. All right, guys. Okay, so I'm going to lean into my heritage, clearly. It's Thursday morning, everyone's tired, hungover, probably a bit exhausted. So who's this good-looking rooster on stage? So I'm the CEO of Interstellar Mapping. We've got offices in Sydney, UK, and in Los Angeles, hence the attire, because we're leaning into both the cash lifestyles. Now, who are we? What have we done? What's our claim to fame? So we were part of the Intuitive Machines Mission 2 last year. We did the ice stability model for ESA. And then this year we've done the site selection, we're part of the site selection team for Argonaut mission. So sites 1 and 2, we helped with that. So this is a pretty dry topic. I'm going to race through as quick as I can through all the boring stuff. At the very end, there's a promise. There's actually something pretty exciting. I think Clive likes to see it. So let's get cracking. Right, so I've got an oil and gas background. I've got 17 years oil and gas. I've got a master's in petroleum engineering. I've got a PhD in mining on the moon. So I'm leaning into my expertise. So what we've done is that we've mapped the moon. So we've done the subsurface temperatures. We can do anything on the moon when it comes to mapping. So DEMs, mineralogy, everything down to 1 meter resolutions, okay? Plus, having the field experience as well, we can develop technologies and we know where that technologies can actually be useful and where those environments are actually going to be helpful when we use those tech. So we'll keep moving because you guys don't want to hear about that. All right. Mate, I didn't make these slides. I'm so sorry. This is definitely not my bag. So yeah, we can find it. We're working on a system. It's currently TRL4. There's no moving parts in the system. It can extract water, and it's a continuous processing system. So there's no on-off valves. And then And then we've got some regolith simulant that we manufacture as well. But you guys don't want to hear about that either. All right, knowing where to drill. Once again, if you have the maps, you know exactly where the resources are. That's our win. So we go down to 2.65 metres. 1 metre resolution, we can go down to anywhere on the moon. But you don't want to hear about that either. All right, from model to mission. Oh man, these slides, I'm so sorry. Okay, a lot of words. A lot of big words for me. I'm a very simple human. So we've got the probability mapping. We can actually go through with our mapping capabilities and go, well, this is going to be the best candidate site for where those resources are. Then we can obviously estimate where the depths, where those resources can be. Then we've got the thermal stability envelopes. So we go, okay, where can they exist long term? And then we can look at those sites that are de-risked. All right. SWES. So I said this is a TRL4 right now. We're extracting about 1 gram per watt of power of water out of simulant that contains 3.5% water content. At the moment, it's 7 kilos at the current stage. We're building it up so it actually can pull a kilo of water out of simulant. It's going to be less than 50 kilos. That's our goal. I actually want to get that down to about 5 kilos in total mass. And I think we can do it too. All right. So using that same system, we can actually identify locations where, so there's all the other nasty volatiles on the moon. So with these nasty volatiles, they're going to impact human health, they're going to impact the infrastructure, etc. So when we have the maps, we can go, cool, we know where the clean water is, clean, or the cleaner. We can identify those regions, we can extract the water out of those regions, and then we can purify it and then get it ready for mission use. For the testing side of things, as I said, we manufacture regolith as well. So there is a problem with simulants that are being used. The other 2 companies that are here too, they would agree with me that the existing simulants can fall short with these problems. So we do know that after simulants get used, they do get rounded, they do get worn. They're not as effective as what they once were. So you've got to constantly change them out. So that's a massive issue, and using the wrong products because it's expensive to get cheap simulants, or affordable simulants, I should say. So leaning into my mining background, we worked with the mining sector, and we've been able to get manufacturing process with them that we can get 50 tonnes of 75 micron, or less than 75 micron fines. And so we can actually then pass on those savings to you guys because we can produce it at cost. So we've got about 40, 50 tonnes at the moment sitting in Australia, ready to go, all bagged up. So we can test with that. All right, sums it up. Cool, we can find it, we can extract it, and we've got the regolith to test it. Now this is my bit. This is my contribution to this. And this is the exciting part. Okay, this is a 3-minute video. I'm coming down here because this is more important than looking at me. Right, so we made a demo of what the capabilities that we can do. So yeah, let's start it off. So what we can do with this is we can look at the temperature at any point on the moon across the entire lunar year. Okay, so as we speak, that's what the data is right now. Isn't that right, Jerry? Rightio. So any location, we can zoom in and we can find that for you. All right, we'll move on to the next bit. I wish I had my computer with me so I could actually do this properly in real time. All right, come on, Nick. Right, so we know the environment's there, so you can go any location that you guys want to go. We can tell you what that temperature is. All right, annual illumination. How much sunlight is each location getting? We can walk into any location, we can tell you what the illumination is at that point. Okay, South Pole. So 3,000 hours to 6,000 hours throughout the entire lunar year. That's the locations. Right, longest illumination. This is the number of continuous hours in any particular day at any site on the moon. Okay, 200 hours, continuous illumination. That's a bloody long time, right? In anyone's books. Okay, the annual illumination, longest illumination was actually what we did with sites 1 and 2 for Argonaut. Now this is where it gets fun. That's a 3D model of all the cold traps in the South Pole between 85 degrees and to poleward. One thing to note, that is not a PSR, and that's a cold trap. Now, what we've just done then when we change those temperatures is that we can tell you exactly where all the volatiles could exist based on their thermal stability. That is everything. That's methanol locations. We also had, where it showed that shell, that was the locations where clean water was with no contaminants. All right, how does it look when we just layer it at depth? That's the water in that zone, in that South Pole, at each depth. We can go through and we can tell you exactly where all those other contaminants exist. I can tell you that over 30% of the South Pole is contaminated with other volatiles that are deadly to humans. Where are we going here? Ammonia. Ammonia is a fun one because we know that that's pretty toxic when it comes into the spacecraft. Okay? We know it's going to destroy things and components. The big thing to note with this, with that toxicology stuff, I've got a few seconds left, is that when you look at the volatiles on the moon, the contaminants, so Orion spacecraft, 9 grams of the Cabeus crater has enough hydrogen sulfide to exceed the allowable concentrations of H2S in Orion. 134 grams of Cabeus crater ejector with H2S is enough to kill everyone on board. So it's actually a pretty big target there. But where there's a bad, there is a positive. Ammonia is great for plant life and biology, and I'm going to get kicked off stage. All right, guys, have a good day. I hope it kept you awake.
All right, thank you very much. I think we have time for one question. Yeah, 2. Okay, 2. So one, really don't see anything up here. Yeah, that gentleman there, and then.
Hi.
Hey, Gal, mate.
Hello, hello. From Chris Giorgio from Stellar Discoveries. We've talked already about some things, but I'm sorry that I'm going to make you not feel good by what I'm going to say. Well, at present, ESA is under patenting a new type of simulants, actually the real simulants, which have been proven that they're extremely activated and they are extremely biotoxic. So during the processing of water extraction, the impurities that you're going to be facing are not going to be only volatiles, but they're going to be also very, very soluble biotoxic chemicals, for example, hydrogen peroxide, and these have to be taken care before the astronauts use the water that you are isolating. So I would say to you to consider another type of simulants available, not the simulants that they are pretty much cocktails from different minerals. Thank you.
Yep. Agreed. Yep.
Jerry.
Jerry Sanders, Ezric. Nick, great presentation. Did you go through and slide all those different volatiles to actually see where some of the other ones are on their own? I've never seen from L-Cross or anything else that there was necessarily pure water, that there would always be some other volatiles there. And so when you mention ammonia, for example, while it's extremely toxic, it also has tremendous value. So when you're doing your distillations, what are you doing with the volatiles that you're not keeping?
We're just focusing on the water at the moment. we have plans to make it a two-phase, and so we can actually split the other volatiles off. But let's get the first step done first, and get the water out. But you are right, though. Is that ammonia is great for plant growth and everything, and so there's a massive opportunity there. Yeah. Yep.
Thank you very much. I don't think we have any other time for any questions at this moment. Sorry. Do we have our second speaker in-house? Yes, all right. So welcome from the exploration company, Cedric Dupont. Cedric is going to talk about key technologies for ISRU-based cryogenic refueling. Welcome on stage.
Thank you very much. Thank you for joining this session today. So I will talk about in-orbit cryogenic refueling today, so it seems a bit far from ISRU, but actually you will see the critical technologies we are developing are really some key enablers and really useful also for ISRU. So this project we have started in Luxembourg is done with the Expression Company and our partner Absolute System. So we decided to join forces to do this project with our complementary activities. So first, the Exploration Company. If you don't know our company, we are developing a cargo vehicle called NIX. So NIX is a large cargo to supply and to go and return from the space stations. It can be launched for every heavy launch vehicle, and this is our main project, our flagship program. And in addition to that, we are developing some future projects on in-orbit services, for the moon, propulsion, and now also some cryogenic activities that we are doing in Luxembourg. For our partner, Absolute System, they are a cryogenic developer since 2010, so they developed, for instance, a breadboard model of a reversible Brighton, technologies that can be very also interesting for space. So this example is for space application. They have also 15 years of experience in cryogenic propellant management. And they have also an ongoing development for a subscale refueling demonstrator, Chrysalis, where we are also part at the Exploration Company for the launch and the mission preparation, together with other partners like the University of Barcelona and Liège. So first, I would like to say that when we discuss ISRU, there is a lot of attention that is done of course, on resource extraction, chemical processing, and propellant production. But producing propellant is not only it's only one part of the challenge. And in reality, what we want to do with ISRU is also to use the molecules. And all this part related to the storage, transfer, you have specific challenges that we'll address in in-orbit cryogenic systems, so in space. But you have the same if you are doing all the complete chain in ISRU. So with the boil-off losses, thermal instability, long duration storage, fluid conditioning challenges, transfer complexity. And without cryogenic management, ISRU will have a limited value because at the end, when you do ISRU, you want that the molecule is used for your applications. And that's, let's say, the second part that we are doing. So I'll not go in detail, but after production, just to see that you have the purification, liquefaction, storage, transfer use. And all these parts actually are really critical and sometimes underestimated, focused mainly at the moment for production. And you need very specific technologies to do that, and that we are doing. So I will go in detail with all this technology a bit after, but really the type of challenges that we'll address, especially the third one, storage, transfer, and use, are really what we are doing in our project. So let's talk a bit about this KRIO-Kit project. So that is done in Luxembourg. So it's a project funded by ESA and LSA to support the development of cryogenic technologies for in-space refueling systems. We are focusing on in-space services and space exploration. However, although it's not the objective of the project, these activities are really a downstream enabler of ASRU. And our objective is really to make propellant, and especially cryogenic propellant, operationally usable in space. And this applies whether the propellant originates from Earth, orbital depot, or ASRU infrastructures. So even if the KRIO-Kit is not producing propellant, it directly contributes to enabling ASRU architectures. And we'll focus on different key technologies. For instance, the first set of key technologies are cryogenic fluid management, reduced or zero boil-off. We say zero boil-off mainly for LOX and methane, reduced for hydrogen, because it's more complex to remove completely the heat from the hydrogen tank, advanced thermal control and liquefaction storage and losses. And this is really some critical technologies, and most of them will be addressed also with our partner, which is some example of modeling activities on cryogenic propellant management, and to assess the boil-off, to demonstrate that we can have the technologies to maintain for long-term storage the tank. And this is one also important part for SIO, because to create the molecule, it costs a lot. It's complex. So you don't want to lose 1 kilogram of oxygen, of methane, of hydrogen when you are doing this SIO. Other set of technologies, you have the cryogenic transfer, coupling interface, field conditioning, autonomous operation, to ensure the usability of propellants. So let me have a look here also on the transfer. Usually the transfer is a very complex problem for cryogenics. It's not only to couple, to have a cryocouplers, and then you pass the propellant inside. All the conditioning, the chill down is really tricky, and you can use a lot of propellant only to cool down the lines and potentially the future tanks. And for the transfer, you need also some standardization. And an example here is the plug-and-play RPOD interface. So RPOD is for rendezvous, proximity, operation, and docking. We are developing this standard interface in an ESA project called INSPOC 1. So you have at the middle the mechanical interface, you have some power interface, data interface, and on top a fluidic zone when you can put storable propellant coupler, gas coupler, or cryogenic coupler. And we can imagine that this interface can be used also for ASRU, meaning you will have the same interface for in space and on the moon, for instance. And so if you have a cryogenic lunar lander, it can refuel both in space and on the moon. And this kind of technologies can really also help to have all the complete chain of ASRU in the future. So when we are doing the SRU need, you know, there is these kitchen engines around liquefaction support, storage, transfer, utilization. And when we are talking about in-orbit, space exploration, and our KRIO-Kit project, we have the same challenges. Liquefaction for us is more cooling ZBO, but behind you have the same technology. You need the cryocoolers, you need a heat exchanger, you need to have a design of tank that can limitate or remove all the heat fluxes that you have. You need long-term storage tanks. You need to have transfers, so with couplers, that in order to use finally your molecule, because at the end, again, for SIO, the objective is really to use and to sell the molecules to different customers and to plenty of a large variety of vehicles. And so our KRIO-Kit technologies really addresses the ISRU bottlenecks. So to conclude some key takeaways, so what I would like that you retain to this presentation is that ISRU is not only about producing propellant. Really, the objective is to be able to use it on different vehicles, and it is all this chain that will make the ISRU happen. Cryogenic management is one of the main operational bottlenecks for future ISRU missions. And finally, our technology that we are developing and in-orbit cryogenic refueling can directly contribute to ISRU ecosystem, and we therefore see strong synergies between this domain and significant opportunities for collaboration in the coming years. So, here are contact details. So for me and our partner, Absolute System. So if you want to have contact to discuss after this presentation, feel free to contact me. I'm in Luxembourg, and I will be happy to discuss with you some future collaboration. Thank you very much.
Great timing. Thank you very much. Couple of questions. Time? Yes.
Jun Shimada from JAXA. Thank you for your presentation. How do you define the system requirements for this element? Because it totally depends on the interface from the upstream liquefaction element and the downstream spacecraft interface.
Yes, and so to define the system requirements, we first look at the in-space application, because for us, the first application for that is really, for instance, you have some vehicles, you cannot send the vehicle full of propellant for instance, the volume of the fairing. So the first application will be to send a propellant vehicle, a propellant tank, then a vehicle, and you refill into orbit. So we have different demonstrations, and I think the first one, you know, we have on another ESA project, we have a value of mass flow rate around 150 grams per second. And so we think this value, and we can go above after, can really also be used for ISRU, because for ISRU, okay, you have the production rate, but after you will need to store these molecules. And so after the mass flow rate, for instance, for the interface to refill the vehicle, will not depend on your ISRU infrastructure, but will depend on what the vehicle wants and have. So if you have a standard interface, I don't know, for instance, let's say 0.5 kilograms per second, you will adapt your system to refill. And what is important is to have some standardization and to have the same refueling interface in your vehicle in order to be refilled in space and on the moon, for instance.
Quick question, quick answer, please.
Great presentation. I want to talk afterwards, obviously. So when you do your propellant transfer, is it a vent fill or is it a non-vent fill when you're going from supply to receiver tank?
Yeah. What we want to do is a non-venting system, yes, to really keep all the molecules. And there is some system, so a bit complex, but what we want to do is really to have a no-vent system.
Okay, because either you slow down the transfer rate or you reliquefy the boil off from the heat transfer. So interesting details. Thanks.
Exactly.
All right, we need to get going. Thank you very much. So our next speaker comes from Imperial College London. Welcome on stage, Kosuke Ikeya.
Hi, good morning, everyone. I'm Kosuke from Imperial College London. And today I am going to talk about how we can make the best decisions for lunar ISRU deployment under demand uncertainty. So this is the day 4 of Space Resources Week already. So I hope that everyone knows that one of the key lunar ISRU products is liquid oxygen. And that's basically why many institutions and agencies are doing their best to extract oxygen from the lunar resources. However, there is a challenge to realize the lunar ISRU plant, which is the market uncertainty in the future. For instance, let's think about the 20 years ahead of the time. We don't know how much lunar oxygen demand is going to be in the 20 years' time in the future. Maybe we might lose some interest in the lunar exploration for some geopolitical issues, but maybe we might thrive on the moon. We don't know what's going to happen. And for terrestrial applications, this kind of market analysis have been done through using the past data. However, in lunar case, we would not have any rich past data in any near future. So that's a challenge we have. So in this research, we use a control technique, distribution robust model predictive control, to help decision makers making the decision for Luna ISL deployment under deep demand uncertainty. So why am I suddenly talking about control technique when I was talking about decision making? Because sequential decision making and optimal control are the two sides of the same coin, basically. So for the sequential decision making, you make decisions, and then we get the new information. And then based on the new information, we make the best next decisions. So this kind of the recursive nature of decision making and information gathering is a key essence of sequential decision making. And on the other hand, for optimal control, let's imagine that we are driving a car. In order to point the car into the next different direction, we need to steer the angle of the handle. And then based on the angle you change of the handle, you get the next state, which is the direction the car is pointing at. And then based on the state, we make the next decision, which is how much we want to change the handle of the car. So basically what I'm saying is that these two techniques or research fields are basically very related to each other. And maybe for the optimal control, decision makings are happening in a more continuous time manner. And I'm going to talk a little bit about model predictive control in this slide. So imagine that we have some past data at time point k. And in model predictive control, we want to predict the future for n steps in the future. This n steps is called prediction horizon. And then what we want to achieve by model predictive control is minimizing the expected cost using this distribution data by changing the series of input decision. And then by implementing the first instance of the series of optimal decisions, we get the next state at the time k+1, and then we re-optimize for the n steps again. A challenge of stochastic MPC or stochastic model predictive control is that we need to have a precise distribution data, which again we won't have for Luna ISL economy. So that's why I use distribution robust MPC. In distribution robust MPC, we consider not only one distribution data, but we actually consider a set of different distributions. And the objective becomes to minimize for the worst expected value considering the set of distributions. And this set of distributions are called ambiguity set. So how can we use the distribution robust MPC for Luna ISL deployment? Oh, imagine that we have this farm that has some architecture on the moon already, and then we have some data set, but only, let's say, 5 data points. So it's a really poor data set, but we need to somehow make the decisions for the next 10 years. In next 10 years, we might want to minimize the cost minus revenue for the sake of get the most of the profit. And the state, instead of the direction the car is pointing at, for the Luna ISL case, the state we want to follow is going to be the production amount of the production capacity of liquid oxygen, for instance, and storage capacity, and also stock level or inventory level. Decisions we can make for the Luna ISL deployment is going to be how much we want to expand at that time, or in terms of the production capacity and storage capacity. And we have some uncertainty that shocks the demand level each year. To solve this as a control problem, we need to kind of consider how the state changes from T to T+1. So in this slide, I'm going to explain one example of the inventory level of liquid oxygen. So first, we need to think about liquid oxygen boil-off. And then we need to add newly produced liquid oxygen from ISLU. And then we can subtract the actually realized demand. So with some minor constraints or assumptions, we can actually make this system state transitions in a completely linear case, which is great news for control engineers. And the objective is, again, to minimize the discounted cost minus revenue, which consists of development and launch cost, which mainly related to the decision we make at each year. We also have the operational cost, which is related to the state of that year. And then we ran Monte Carlo simulations of 25 different cases or demand realizations. And I compared the result for other 3 techniques. So on the most left, you can see the distribution robust MPC case. The first, how you see this figure, like the smaller the number, the larger the negative, it's better in terms of the performance, which means more revenue, less cost. First, what you would notice is that for reinforcement learning trend policy, it shows a lot of the positive numbers, which means a lot more cost compared to more cost than revenue. So it's not good for firm. And then maybe you might think that this deterministic MPC, which is decisions that we make without considering any uncertainty, might actually work the best in terms of the mean value. Yes, in terms of the mean value, that's true. But however, for the deterministic MPC, it suffers from the huge supply shortage. So when the supply shortage is actually critical for safety reasons or many other reasons, actually it's not a good case to use the deterministic MPC. The conclusion here is that the distribution robust MPC actually works good enough or competitively against other methods while satisfying all the constraints. So to summarize, in order to address the lack of historical data in lunar economy, we use distribution robust MPC. And the result shows that distribution robust MPC works as good as well as many other methods while keeping the constraint satisfaction. And future work includes sensitivity analysis on discount rate, for instance, and prediction horizon time length. And that's it. Thank you for your attention.
Thank you very much. Any questions? While they're thinking, I might have one. Maybe it's a naive one. How big is the model? How big? So how many parameters you have on the technical side and on the economical side?
Well, it's a huge model. So for the economical side, we need to assume the cost of the developing ISLU, operating ISLU, and so forth. So we have and also the parameter for the discount rate as well. For the technological part, we need to have some parameters, so the specific mass of ISLU plant or energy systems, as well as the specific energy density and so forth. So those there are a lot of parameters. So we use those numbers from the past literature mainly. Yeah.
All right, say 40 parameters.
Maybe 40, yeah.
All right. Any other questions? Yes, and quick one, and then another quick one. Thank you.
So, very unconstrained model. What would it take to constrain it? What would be the 1 or 2 things that would help you constrain your model?
Help me constrain the model in terms of
being such an academic exercise, but actually pointing towards a system that could actually be developed on the moon and actually generate money. What are you lacking to constrain that model is what I'm asking.
So the constraints that I use in this model is mainly that, for instance, demand is usually always met. So like I use a chance constraint that like more than 95% of the time the demand has to be met. So the stock level has to be larger than the demand, for instance, those are the constraints I use for this model. And then, but we need to add some like economies of scale, for instance. That's something that we need to address in terms of the future direction. Yeah.
There was another one here first, sorry. Quick one, please.
Yeah, thank you very much for the presentation. Two very short questions. First of all, you're working on the demand side, but offer can also create demand. So if there is availability of technology, it will drive demand. Is that factored in?
Yes, that's a kind of future direction as well. So our model just treats demand dynamics as a kind of exogenous. So the decision does not affect the demand. That's an assumption. But then obviously, what happens in reality is like as technology develops, the demand changes as well. So that kind of interaction between the architecture size, decision making, and demand should be modeled in the future.
Okay, thank you. And then a very short one. You focus on liquid oxygen and energy. Why not everything else? Because there's 25 other technologies that you could apply exactly the same.
Well, this is. Well, I use liquid oxygen and energy because I think that I thought that was probably the one that gathers the most attention. But obviously, this technique itself does not limited to like specific technology. As long as we can model, like as long as we have like specific mass of ISLU plant and so forth, we can apply this technique to any other architectures. Yeah. Thank you.
I'm sorry, we need to move on. Thank you, Kosuke. So, next speaker from University of Bologna and Italian Space Agency, Matteo Curcio. All right, stage is yours.
Thank you. So, hi everybody, my name is Matteo Curcio from University of Bologna, and today I'd like to present my latest work in development at the Laboratory of Industrial Safety and Environmental Sustainability in collaboration with the Italian Space Agency, which I thank so much for the continuous support they are giving to this and also my other works. So, okay, that's it. Basically, oxygen, we know it's really important because we need to breathe it and we need it also as a propellant in liquid rocket engines. And let's suppose we want to go to the moon. Okay, so we need the oxygen on the moon for long-term duration missions. And we have two choices here. We can bring oxygen from Earth with us on the moon, but that is a really expensive option, okay, because it costs up to 100,000 euros per kilogram. Or we can produce oxygen directly on the moon with in-situ resource utilization technologies. But the main issue is that on the moon we have a really hostile environment, scarcity of resources, and to understand properly the environment, we need the expertise from the space sciences. Okay, so on one hand, we need to understand the environment, to know the environment, and on the other hand, we need to build, to design processes and plants that can meet in the best way that environment, those constraints. So we have on one hand space science, on the other hand chemical and process engineering, which has got more than 100 years of expertise on Earth on process design and optimization. And in this increasingly growing overlap between space science and chemical engineering is thriving a subject of a really recent introduction, which is astrochemical engineering, which I believe in the coming years will prove more and more important. So, back to it. We talked about environmental constraints. Just to refresh it a bit, on the moon we have high thermal excursion, almost no pressure because we have no atmosphere, reduced gravity, radiations, and of course, the protagonist of our vulnerability analysis for now, which is impacts. Okay? On the moon, we have impacts almost every day, and so when we're going to be on the moon for not 2 weeks, but for months, for years, we need to take the vulnerability of the facilities towards these impacts into account right from the start. So with these premises, we want to integrate reliability and also resilience drivers in early stage design of in-situ resource utilization facilities and processes in particular. And to do it, this work started with 2 steps. Okay, so first we developed a simplified vulnerability models for the impacts, and then we applied the vulnerability model to 2 different process architectures, which I'm going to present in just a bit. Okay, first of all, we said we need to produce oxygen. How do we produce it? This actually comes from another one of our works, which is going to be published shortly, which is a multi-criteria assessment for the processes that have the aim of reducing lunar oxygen. And we found out that from a process perspective, electrolytic and pyrolytic processes work generally well than reductive processes, which are the ones that need a chemical agent brought from the earth, so hydrogen or methane and so on. So then what we did, we focused on the multi-layered structure, and we took the process in particular consideration, and we decided to analyze for our first iteration, let's say, the molten regolith electrolysis process and the carbothermal reduction process, because they are the 2 most representative candidates of the electrolytic and the reductive processes. So we made a map. This is a really simplified slide, but basically we distributed the equipment on the lunar surface based on this grid. We took mainly configurations that were already present and validated from literature. And then, with a Monte Carlo-based approach, we started raining objects on our grid, and on the left side, which for you I think is the right side, well, on that side, you have the example of an impact on the equipment. So the impact has happened in the central point of the red cross you see, and then you have all the effects on the surrounding equipment. But which effect in particular? We, for this simplified model, consider 3 different failure modes for now. The first one is the so-called basin fall, so we do not have a direct hit of the object towards one of our equipment, but the impact causes a crater to form, and then the equipment falls inside the crater. And this is not a scenario in which you have the sure failure of the equipment. It's just a 0.5 probability, because we consider that there could be some possibility of recovering it almost immediately if it just fell a bit inside the crater. Then we have a direct hit from the meteorite, which of course is followed by a complete and certain failure. And then we have a secondary hit, which can either come from the ejecta of the impact itself, or from what on Earth is called a domino effect. So basically, our first equipment gets hit, and then it shatters, and the pieces of the first equipment hit some other equipment. So, occurrence of the failure. For impacts, we investigated that we have a 10 to the minus 5 events per year, and for typical failures, so for example, a pump which is not working anymore, a compressor which is not working anymore, we have 10 to the minus 2. But the problem is that the impacts are so-called high impact, low probability scenarios. So when an impact occurs, you have much more risk than for a complete failure and loss of function than you have with a typical occurrence. Severity of the failure, we consider a real common KPI, which is the time to recover. And I haven't put any number in here for now because I didn't want to bias you. So I just said that for the carbothermal reduction, we investigated and we found out a higher time to recover than what we found out for the molten regolith electrolysis. And again, I haven't put any number in the slide because for the publication, I will need your help. So please raise your phones, scan the QR code, and you can also compile the questionnaire when I've ended my talk. And we, as it has already been done some years ago for process plants and for the industrial facilities on Earth, we want to conduct an expert questionnaire which will be the base for the final assessment in the publication that would follow this work. So I leave it here for some seconds more, if anyone else wants to scan the QR code. Okay, thank you very much. Then if you want to share it with some other experts, you can contact me. I will be really happy to answer. So going to the conclusions and further developments, reliability must be taken into account from process and architecture design, so from the earlier stages of the decision-making in situ resource utilization. And we found out for now that processes not relying on Earth resources are less exposed. For the future work, we want to include some different scenarios in the models, moonquakes in particular, and we want to actively integrate reliability and resilience in early stage process design. So we're going to propose some novel architectures and processes based also on the reliability and resilience indicators that I showed you before. So this is it. Thank you.
Thank you very much. We have 2 minutes or something like this for questions. I don't see, yeah, yes.
Yeah, Clive Neal, University of Notre Dame. So in your impact modeling, what size of the impacts are you using? Are you using the current impact rate and impact size that we've been seeing through LRO? Or are you just assuming a given mass of the impact?
We based our investigation on the information that are contained in the Lunar Sourcebook and some other publications that came after. And basically, we're considered as impacts everything which is bigger than the dust.
Okay, but I would suggest you look at the LROC catalog of recent impacts on the Lunar Reconnaissance Orbiter to get the size and mass of those impacts that are happening now.
Okay, will for sure. Thank you so much.
Anybody else? No? Speak now for there, sorry, thank you.
Hello. Astrochemical engineering is something that it's already going on. I have heard about astrochemistry, but I don't know if you're already an astrochemist or something like that.
Okay, thank you so much for the question. Actually, I'm not an astrochemist. I am a chemical engineer, and I understand the confusion sometimes, but astrochemistry is a science, and it studies like the chemical composition in space and the chemical composition also of the forming stars, the nebulae, and so on. On the other hand, this is an engineering field. So one is science, and I'm pretty ignorant myself in that field in particular. This one, on the other hand, is like the application of the chemical engineering principle in space. Thank you.
All right. Thank you very much.
Thank you.
Do we have our next speaker in-house? Kiho? Yeah, all right. So from the JGC Corporation, Kiho Fukaura.
Yes.
Is that right?
Yes, perfect.
More or less. Thank you. Stage is yours.
Thank you. Yeah, so good morning, everyone. My name is Kiho Fukaura from Japan, a unit leader of the Lunar Plant Unit at JGC Corporation. So today, I would like to present an overview of JGC's current activities and concept regarding a water-based ISRU plant mainly. And please note that this presentation is intended to provide an outline of what JGC is currently working on. So for any technical details not covered today, I would be happy to discuss those separately afterwards. So let me start with a brief introduction of our company. JGC stands for Japan Gasoline Company, and we are a global engineering company established in 1928 with nearly a century of experience as an EPC contractor. It stands for Engineering, Procurement, and Construction in oil and gas field. And we have delivered more than 20,000 projects in over 80 countries, including projects in harsh and remote environments, such as desert and permafrost regions and offshore areas as well. So this experience forms the foundation of our approach to lunar infrastructure engineering, and our business covers a wide range of fields. These include energy transition, industrial and urban infrastructure, as well as functional materials and resource recycling. So lunar development requires the integration of multiple disciplines, and JGC's strength lies in system integration across complex infrastructure domains. And more specifically, we engage in areas such as LNG, CCS, chemical plants, hydrogen, water treatment, smart cities, and recycling technologies, so many. So we believe that lunar infrastructure is not a special case for us, but an extension of complex infrastructure system we already designed on the Earth. So definitely our next target is gonna be the moon. Again, we do a lot of projects all over the world, including at the jungles at East Asia, as you can see there, and at the desert or Middle East and permafrost at the Russia area. So the moon gonna be the next. And this slide shows our vision of named humanity, which stands for Lunar Smart Community, we called, optimized around the lunar ISRU plant. At the center, you can see the lunar plant, ISRU plant, is located that extract water from polar regolith and providing a propellant to lunar spaceport above. And this water supports not only propellant production, but also the life support and habitation systems as well. So the ISRU plant acts as one of the core infrastructure for this kind of lunar community, we believe. And for the existence of lunar water resources, as you may already know, but for the polar region, there is a potential that the water is existing there. And these areas may be the key candidate for future lunar-based ISRU deployment. And also in the I-60 Global Exploration Roadmap 2024, ISRU on the moon is clearly identified that it's gonna be the key element. So As already discussed here on this conference, the exploration strategy is shifting from bringing everything from the Earth to produce and circulate resources locally on the moon. And this slide illustrates how ISRU enables resource utilization on the moon. Water extracted from the lunar ice is purified and electrolyzed into hydrogen and oxygen, and after the liquefaction, we can get the liquefied oxygen and liquefied hydrogen. And these products support the rocket propellants and fuel cells, life support systems, and human residence facilities solely. And in addition, for the above, lunar minerals can be proceeded into construction materials and infrastructure components as well. So this concept is not only theoretical for us. Actually, we started since 2028. We have been working with JAXA on the conceptual study of lunar ISRU plants. Our activities covers system studies, demonstration planning, and the design of terrestrial pilot plants as stepping stones towards lunar deployment. Also, in parallel, we have collaborating with industrial partners such as Yokogawa Electric to develop the ultra-remote plant control system suitable for lunar environment. So reliable automation and autonomous operation are essential for future lunar infrastructure for sure. And for the mobility side, we also involved in project related to pressurized rover, which Toyota and JAXA is proceeding. And mobility is a critical element connecting ISRU plants, habitat area, and exploration site as well. And in addition, through a project led by Japanese Ministry of Agriculture, we are also involving in the study of resource circulating food production system as well. So this contributes to sustainable long-term human presence on the moon. And altogether, these activities position the lunar ISRU plant as a central infrastructure element on the lunar base or lunar environment. So it supports energy, life, and mobility and expansion. And here, this slide summarizes JGC's step-by-step study record with JAXA. So again, from 2021 to 2022, JGC and JAXA conducted a conceptual study to define the basic architecture of a lunar ISRU plant utilizing water resources. In this phase, we clarified key system elements and major technical challenges. And in 2023, the focus shifted to a lunar pilot plant concept where we studied the overall system configuration and possible demonstration scenarios toward lunar application. And 2024, we started the conceptual design and breadboard testing of the terrestrial pilot plant, including experimental verification of water extraction from hydrous regolith. And currently, from 2025, we proceeded the preliminary design phase of the terrestrial pilot plant. You can see how it looks like on the 3D model here. And this one is already shown at the first day presentation from Jun Shimada-san by JAXA. And so through these activities, we are steadily building the engineering foundation necessary for future lunar deployment. So this is kind of our roadmap towards the 2024 that we desire to operate our plant systems. So the goal is definitely functioning this kind of plan step by step. And this is kind of summary and seeking for the collaboration things. So JGC is a global engineering company, particularly in large-scale and complex infrastructure projects, often in harsh and remote environments. So by rebuilding this experience, JGC, we are now contributing to lunar infrastructure development, mainly in Japan, as a system integrator with a focus on lunar ISRU plant. So, but rather than developing these kind of things in a single technology in isolation, our approach is to design a robust and scalable and operable system with you guys that can support long-term human activities on the moon. So we are particularly interested in collaboration related to key element technologies for lunar ISR plant, human habitation systems, autonomous and operation control, and integrated infrastructure concepts. So if you see potential synergy or complementary expertise, we would be really happy to discuss for the possible collaboration and explore how we can work together. So our vision is quite simple, aiming for building the infrastructure on the moon. And thank you very much for your attention.
Spectacularly on time. Thank you very much. Any questions? Do you all want coffee, I guess? So maybe just a quick one. Maybe I missed it. So when do you plan to open to third parties? If you can open to third parties, the pilot plan? When is it supposed to be opened?
Oh, we are still open. Yeah, so I mean that open every time, but
on ground.
Yeah.
Okay. Another question? Yes. Thank you for pointing.
Hello. I have also a quick question. If I would like to propose a project, and I know that you are from Japan, right?
Yes.
Japan agency. It's a little bit complex to work internationally, but you would be open as well to work from someone, I don't know, from Mexico?
Okay. Yeah, sure. Yeah. Let's discuss with our team first. And we have branches in UK and United States as well. So we have a global branches and we can connect together. So let's have a discussion first and making a seed of collaboration and how and clarify how to proceed together afterwards.
Also, I have another quick question, and it would be, your company is thinking of establishing a chemical process on the moon.
Yeah.
A base, but basically chemical processes need rigorous containers and stuff like that.
Yeah.
I saw you had some basic components which you could build, but in this case, is your company already having an idea of how will they develop this equipment in the moon, or is that not already thought?
We are proceeding this kind of a component design by us at first place and seeking the manufacturers to make it happen really. So we are seeking the partner all over the world for that. Yeah.
Thank you.
Any other quick question? No? Yes? Yes, down there.
Hello, my name is Bjørn Elseth from Norway. We have a lot of oil and gas industry in Norway. Do you have any current European oil and gas companies involved or talking to, or can't you say anything about it?
Actually, no yet. So if we have a chance, it's gonna be highly appreciated.
All right. Thank you very much.
Thank you.
Last but not least, from Sagittarius Logistics, Jonathan Slavik.
All right, well, good morning, everyone. My name is Jonathan Slavik, and I am the CEO and co-founder of Sagittarius Logistics. And I want to talk to you today a little bit about a piece of infrastructure, one of the ancillary components to space resources, an enabler for space resources that is really missing in the EU, and talking a little bit more about why it's important and what it can really add. So, one of the main challenges we face with ISRU is that we need precision landing to get nearby to the resources, right? If you're landing kilometers or even hundreds of meters away from the resource, you're going to have to traverse really far. You're going to have to, be able to set up your pilot plant wherever you're going. You need to be able to land right where the resource is. Otherwise, none of these other architectures work, whether it's prospecting, whether it's extraction, all of this, it's absolutely critical to be able to have that. And we have to be able to validate that, and we have to be able to make sure that we have the capability within Europe to do that kind of precision landing. So the good news is that Europe does have this technology, right? We have an exceptionally deep bench in terms of terrain relative navigation, LiDAR, event-based cameras that are being developed right now. All of this technology is funded, it has institutional deep knowledge, it's contributing to things like the Argonaut program and all the other landers and technology that are being developed here in Europe. But the problem is that technology is stuck, right? There is a significant TRL gap. Sometimes we call it the TRL Valley of Death, where we're looking at all of this technology that's been funded, that's been developed. It's been developed in the lab, right? It's been developed on things like the Tron arm, where we can fly over a simulated lunar field and make sure that our TRN systems, all of that stuff works correctly. But what it doesn't do is it doesn't replicate for us the actual flight environment, the vibrational loads on a landing, lunar lander as it comes to the surface, the dust kicking up, the plume environments, both gaseous and thermal, all of these loads that we really need to be able to validate that our systems are robust enough to get this ISRU technology on the ground at the exact position it needs to be to develop value. And that's something that has never really been able to be developed in the EU. So how has that been done in the past? Well, in the US, a lot of this technology has been developed on VTVL, or vertical takeoff, vertical landing test beds. Some of them that you might be familiar with, the SpaceX Grasshopper is a great example. Not ISRU, but a system that was used to validate precision landing for those drone ship landings that they do. There was also the Morpheus program that spun out of NASA that was able to validate autonomous hazard avoidance and really get us to the place that we are today with lunar landers and Martian landers. But there's one I want to dwell on here that I think is really important and illustrative for this ISRU group, and that is the Honeybee PlanetVac system. So Honeybee developed PlanetVac for regolith sampling, and they developed it in the lab. They got it as far as they thought they could. They solved every problem they could possibly think of, but then they brought it out to a group called Maston Space Systems, and they were actually able to put it on the foot of a lander, have that lander propulsively land with the foot in lunar regolith simulant. They sampled over 300 grams of that simulant and flew away. And the system worked, but they learned a lot about what did work, what didn't work. They were able to take that back to the lab, use the things that had been validated, and fix the things that didn't work. And then now, last year already, PlanetVac actually flew on the Blue Ghost mission and was demonstrated on the moon. That is the fly, fix, fly loop that is missing in Europe. We have all of these fantastic technologies for precision landing, as well as for ISRU, sampling, prospecting, all of these things that we think will work, but until we get out there and we do that fly, fix, fly loop, we don't really know what the technology is and how it's going to perform. And right now, we really have a gap, right? There's a problem that, there are vertical takeoff, vertical landing capabilities within Europe. We have things like DLR's Eagle, but that's jet-powered. It doesn't necessarily represent what the environment's going to be like. Gruyere Space Program out of Switzerland was able to do their own vertical takeoff, vertical landing rocket, but that wasn't commercialized. They moved on to other topics. So this capability has never really been here, and then to go to the US to use that capability that's been developed there, we run into all sorts of export restrictions, right? You're flying your engineers across the ocean. You have to give your data over to another country. A lot of it is export restricted. You can't get all of the data back, and it's not a real play for sovereign capability. It is not something that we can trust to develop European domestic capability going forward. So that's where Sagittarius Logistics comes in. We are the team that developed US-based vertical takeoff, vertical landing technology. Over 600 landing flights that we were able to do. We've done things like flying 12 times in 5 days with the same team on the same vehicle, demonstrated sub-centimeter landing precision. And we're building those vehicles in the US right now, and we're looking at how are we going to incorporate that into a European entity where that vehicle can be exported one time, it can live in Europe, it can be owned here, and it can be a sovereign capability that accelerates the development of all of the domestic capabilities that are being developed here in Europe, and do it in a way that's a little bit more future-proof than even the way things are done in the US right now, using cryogenic propellants, using deep throttling, so that when we look at the future of how things are going to be landed on the moon, we make sure that those technologies are being tested in a way that's representative. So where we are right now is in the US, we're building a ground test article, getting that firing ideally later this year. We'll see how that works out. We've got the engine already sourced there. You can see I've got the first article there holding it. We've got a video or an image there of the engine hot firing. So we're moving very quickly to building our first vertical takeoff, vertical landing iteration using this engine. We're calling it Cuyahoga, named after the US National Park. But most critically, we're building a number of tail numbers of these vehicles, right? We're building a lot of them, and we will be setting up here in Europe to be able to fly that vehicle and have it, live here, operate here, iterate here. Maybe it's transitioning over to an EU or ESA member state developed engine. It's utilizing more of the, sensors and things that are developed here, so we can do, what has been done in the US can now be done in Europe, where we have an open software architecture where an actual GNC profile and control algorithm developed here can be integrated directly onto the rocket, can fly the rocket, can control everything, can take all of that sensor input, can do all of the sensor fusion, experience all of the noise, the vibration, the failure modes that are going to exist as you do propulsive landing on the moon, and we can validate that we know it's going to work here before we are going to the moon, we're going to these resources, and we're trying to land precisely at those resources. So all the work that everyone has been presenting here this week can be properly placed to be able to actually, do what everyone is so excited about in terms of extraction or prospecting and, laying the groundwork for human habitation. So that's something that, if we're really serious about ESA going back to the moon and having this domestically developed capability, we really need to make sure that we own the entire fly, fix, fly loop so that iteration can not only go quickly, but can be guaranteed. So with that, my name's John, and if you're developing anything for precision landing, terrain relative navigation, LiDAR, systems like that, that you need tested, that you want to know are the most reliable and you can give to your partners for landing with the confidence that it's actually going to work, I'd love to chat more, so please reach out.
Thank you. Questions? Don't see which. But so first of all, how big is that? So what's the payload capacity at the moment?
So the payload capacity for the European operating vehicle is about 200 kilograms. And the vehicle envelope right now is being able to go up to 2 kilometers in altitude as well as translate 2 kilometers from point to point. However, we don't necessarily need to use that entire envelope on every flight. So there are flights like the Honeybee robotics flight that I was talking about with PlanetVac. That only had to go up maybe 5 meters in the air just to clear the landing pad and then come back down to sample that equipment. Versus, when we're working on things like NASA Splice, that obviously has a much higher altitude because it's a entry, descent, and landing profile. So the payload capacity is large enough to be able to do any of these systems, but not necessarily, huge in another sense, enough for subsystem development.
Questions in the audience? No, maybe they all want to go to coffee. Yes.
Thank you for the presentation. Simone Pirotta, Italian Space Agency. I'm curious to understand if the architecture to acquire sensors of the GNC, or do you need any other ground equipment, or is everything stored on board and managed on board?
Yeah, so in terms, and I think I interpreted the question being, do we do everything on board of the vehicle, or is there a ground component to this? The answer is it's very flexible. As a testbed platform, we can do either of those. There may be a situation in which you want to test the resiliency of a telemetry downlink system, right? In that case, we would definitely record on the vehicle to have a source of truth, but then we would also be able to test that downlink system and say, hey, is there any RF interference from the ionized gas flow coming out of the rocket engine? Is the plume interfering with any of that? Can we validate that a ground system is working correctly? So it's a very broadly applicable way to validate so many enabling technologies within the precision landing chain that are critical to enabling space resources.
Yes, there is. No, sorry, I think I saw that one first, right?
Yeah, hi, John. Very nice presentation. On this precision landing, will you use kind of existing concepts like they've done at SpaceX and now Blue Origin, or do you develop something new? Or can you say a little bit more about that?
So I heard most of that, but develop which system?
The precision landing.
Oh, precision landing. That's something that our team has developed and actually is the originator of that technology in the commercial industry. So the team pulls a lot of, our CTO was the first one to develop successfully a commercial precision propulsive landing system. It's the system that SpaceX copied. Blue Origin has their heritage goes back to a different location, but that's something internally that we've developed that we're very excited to be able to share the capability of. We can't necessarily share that algorithm and how we actually do that, but we can use our performance with those precision algorithms to validate other algorithms. So I know we're a little bit over time, but one of the really exciting things is if you have your own precision landing GNC algorithm that you've developed, our vehicle, like I said, is an open software architecture where we can be a wrapper that's a little bit of a black box around that technology. So you can fly, your precision landing can fly the rocket, can validate that it's coming down, and if it says, something goes wrong, it decides to try and flip the rocket over, our system takes over and says, okay, that's getting it's too much, let's land and try again. So you're not necessarily risking all of this hardware to be able to develop the software, even if we're not able to share the details of how we're doing it with the client.
All right, I think that's it. A big round of applause for our speakers.
Yeah, thank you very much.
Enjoy the break.